Good morning. Hello.
Good morning.
Something's going on with my video. Video settings, integrated camera. I think we're going through the same motions as the other. For some reason, we don't have my camera this morning. And it's not the same problem as I had the other. Okay, well, good morning, everybody. Even though you can't see my face, I don't quite know why. I'm not going to spend too much time investigating right now. Yes?
Yeah, I think it's from your keyboard. I think that's like what happens when you press the. It's like a tab from your keyboard.
All right, let me go down. I'm guessing I had some little helpers. Let's see. Maybe F8. That's what it is. Thank you. The problem is, like, if I don't press, well, now maybe this part. There we go. Here we are. Good morning. Thank you. So it's F8.
Yeah, you're welcome.
Which, since I didn't press it, I didn't know that could be an issue. The other one that I was playing with is the one that is actually above the camera, the little thing. Well, thank you. We're learning something new every day. How's everybody this Monday morning?
Doing good.
I hope your coffee is strong or whatever you use to get up. Yes, I'm working on my second tea. I had little helpers wake me up at 6 a.m. this morning, so I do need some strong tea this morning. Anyway, all right, let's get going. Today we are wrapping up heat transfer. So essentially, we're just going to mention how do equations of change look like when we actually have change in time. And technically, the way one develops those equations is similar to the shell balance that we've been already working on. Let me share my screen. All right. Okay. So we're just going to quickly recap what we've done so far, just as a general broad review. And then we're just going to mention how equations look like. Warning, they do look a little scary by the end, but again, they're just equations. And remember that you have gone through all of the steps of developing those equations already. So there's nothing really new in there. It's really just for the completeness. And then after we complete this energy transport, then we're going to move on to component balance or mass transfer. And a lot of those equations will look familiar. It's just that the notation will slightly change. Also, as a practical matter, basically energy or heat transport, whatever we complete today, that's what's going to be on the exam next week. So we already have this 1 week of in between. So essentially, porous media or whatever we've done for porous media flow and heat transport will be the topics on the exam next Monday. And I still owe you a quick information on Proctorio and how to set it up inside of Canvas if you haven't already. So I'll complete that by the end of the day today. All right, let's get going. So we started this lecture with Fourier's law of heat conduction, which is the simplest case of heat transfer when I have solid, nothing's moving, no flow, and I have a temperature difference. So in the simplest of the cases, as far as geometry goes, we think of a parallel plate or a plate of a material. So this is our equivalent of the parallel plates for flow problem. And they're separated with the distance y. We have certain area on top and bottom. And we initially have both of them at the same temperature. And then we, at a certain time, raise the bottom plate to a higher temperature, T1, and wait for temperature to equilibrate. And assuming we keep that bottom plate at temperature T1, there will be a steady state profile that develops, and basically I'm going to have a linear distribution basically between temperatures T1 and T0 at the top. Okay. And again, that requires that we keep the bottom at T1. Now, the simplest model for this transfer is the one that's basically is a relating flux. So this is my heat flux per area, we typically normalized by area, is proportional to this is essentially derivative, what ends up being a derivative or the difference in temperature divided by the distance. And the coefficient of proportionality is thermal conductivity. So that basically results in my 1D Fourier law. And essentially, there's this minus that shows up because basically this is T1 minus T0, but this T1 is at the lower y and T0 or is at the higher. So basically that's how I get this minus here. I always flow from higher to lower temperature, whereas all of the coordinate systems point from lower to higher. So therefore we have a minus here. So in the simplest of the cases, my Qy, that's my flux per area, heat flux per area is minus K dt dy. And if I put that in apply that in 3 dimensions, that basically X, Y, Z components of heat flux are equal to minus K X, Y, Z components of gradient of temperature. So basically my equation is that Q as a vector is minus K gradient of T. I could have that generalized more, but these are not typically the cases we're going to deal with. And then we have units of thermal conductivity that basically I resolve from this equation. Does anybody recall what those units are of thermal conductivity K? Can you flip through notes and find out? All right, watt. So watt is basically joule per second per meter per Kelvin. All right. Oops. Meter square or meter? Hmm? Well,
It
you're
should be meters squared.
Meter squared because it's per area, right? Anyway, so, but again, if you don't remember, this is, remembering equation is slightly easier, I think. Then you can always plug things in. Now,
Question.
thermal diffusivity, yes?
So why would it be meters squared? Because isn't the divergence?
Oh, maybe not. Let's plug that in. Is my coffee strong enough? So we have joule per second per meter square. But this is Kelvin per meter. Okay, my bad. So it is per meter. So anyway, always remember to plug into the equation. All right, thermal diffusivity is just something that we kind of normalize this thermal conductivity with, so that we kind of factor out the details of the fluid. So there is the fluid parameters here, rho and Cp, that I normalize it with, and then I have this normalized units of thermal diffusivity, which are in meters squared per second, and that enables me to compare different types of transport. So I will compare typical Prandtl number is the kinematic viscosity, which is also in the units of meters squared per second, divided by alpha. So this is a dimensionless number, and Peclet number is Reynolds number times Prandtl number. So these are the numbers that tell me what is the dominant mode of transfer. So Prandtl number is in the simplest case when I just have looking at the diffusivity versus kinematic viscosity within a fluid. And this basically also takes, so this would be typically looked at in laminar flow regimes. And this Reynolds number also brings in the type of the flow that is happening as well within it, because if I have, for instance, turbulent flow, that will take the cake, and no thermal diffusivity simply cannot compete. Okay, so when I look at the comparison between energy and momentum transfer, we typically need a difference in velocities to actually have momentum transfer. So my driving force is gradient of velocity. Velocity, however, is a three-dimensional, it's a vector. So it's a three-dimensional field. Gradient of that three-dimensional field, I need a tensor to express it. So that's why my stress, tau, is a tensor. The transport coefficient that basically just defines the fluid behavior is typically a scalar though. Now, in terms of heat transfer, I need temperature differences. Temperature is a scalar field. So basically my flux is expressed as a vector, not as a tensor. And my transport coefficient is thermal conductivity. There are certain similarities. So viscosity of gas at low density increases with increasing temperature, and so does thermal conductivity. Whereas viscosity of liquid decreases with increasing temperature. That's like if you heat up the oil on a pan, it's gonna flow easily. Thermal conductivity of liquid also typically decreases with increasing temperature. However, that's for most liquids, it can be quite complicated behavior. Now, what we monitor in shell balances is so-called combined energy flux. So my Fourier's law, it describes what happens if I just have temperature difference and nothing else. If I also have fluid, for instance, flowing, that complicates things. So for one, I could simply have fluid flow into my, just like I'm flowing in right now into my frame that is static, and that brings the energy with it. So this is this first term of the combined energy flux, which is simply, this is kinetic energy plus internal energy carried in with velocity v. So this is so-called convective portion. Then after that, I also have the fluid within this frame. So I am in this frame, and it seems that I never know where my camera is. So basically, I am in this frame, but inside my fluid, I have differences in velocities. And those forces and between my fluid layers and the forces that exist in my frame, they're doing work. And that work could produce heat. And this is the second part. This is basically work of the molecular forces that exist within my control volume. So that if you remember, we had that large tensor that had both the pressure pressure times identity matrix plus shear stresses. That was my vector P dot V. So this is the work of molecular forces. So that is my combined energy flux. And that's what makes resolving or computing what these problems a little more complex, because I have to couple what happens with the flow as well as so both momentum and heat transfer. So when we have different versions of this. So this is the first version, the one that is actually more convenient for actually solving problems is the one that involves enthalpy. So basically the pressure term has jumped under here, and that forms so the internal energy plus the P pressure times V, that basically forms enthalpy here. And that's a little easier to then resolve and solve for. So we need to, what I'd like you to basically understand is what these parts of this combined energy flux are. So we have convective part, we have the work of molecular forces, and then we have the classical Fourier's law that is just heat transfer because of the temperature differences only. So if I'm doing a shell balance, I will look at the rate of accumulation of energy, both kinetic and internal, within the fluid element. And that is equal, basically, net rate of this combined energy flux that has these three components: convection, heat by molecular transport, and work done by molecular transport. So those are the three that are described by my vector E. And then I also need to add work done by any external forces, as well as net rate of energy production, or might be the other way, within the element, okay? So I typically look at my volume element, and I will look at opposite sides and do this if this is Cartesian coordinate system. I will balance this on all sides. So this, I'm looking at the X direction, and I have to take my energy fluxes per area. So I have to multiply it by area in order to do this balance. Okay? And you can do this in any coordinate system. This is just an example for Cartesian. Okay. So the one example that we had was this viscous heat generation in a very thin shell. So I'm not going to look at all of examples, but these are some of the examples that we had. So if I have annulus and the outer part of the annulus is rotating, inner part is static, this is what we called Couette flow, and we actually had the solution for this in a cylindrical coordinate system than previously. Now I can also look at what happens if I'm keeping the inner cylinder at temperature T0 and the outer at some different temperature TB. So I have now coupled heat and momentum transfer. The way we simplify this problem is by looking at the thin shell of thickness B this time. So it used to be between kappa R and R. Now we're just simplifying and saying it's a shell of thickness B. And for large curvatures R, we can ignore the curvature. So we can pretend that this portion here is straight. And that's what's plotted here. And then I'm also changing then coordinate systems. So what used to basically be my theta direction becomes a Z direction. So that's this direction along this cylinder here is Z. And my cross direction, or what used to be radial direction, is X direction. And X simply goes from 0 to B. I'm also further simplifying what used to be a nonlinear velocity distribution. I'm just simplifying it to linear one from 0 to omega r, which we call VB. And that's shown here as a velocity profile. And the way we solve these problems is that we know what velocity profile is from momentum transfer already. And then I use that in the balancing heat transfer. So when we solved that problem, and this is the part that you plotted for an exercise, we basically got, if I didn't have any temperature difference, then I would still have some actually change in temperature because of the viscous heating, and that's given here. So basically that profile would go from T0 back to T0, and I would have some maximum here in the middle, okay, essentially at B/2. Okay? And that's given with this equation. If my temperature TB is actually different from T0, then this profile will look approximately like that, and that's given with this formula. So it's important to understand that there's always a little bit of viscous heating. It's just that in momentum transfer, when we just looked at the velocity distributions, we were ignoring it. So you will always have these contributions, and often you will ignore them either because they're not important. If that is a very relatively small temperature difference, it's not going to change your viscosity. That's not what you're actually tracking, or that type of energy dissipation is not something that you're trying to measure. Then you can simply proceed and ignore. But in certain problems, if this is a very thin shell and I have lubricants in various machine components, this can be pretty important. So we actually need to know what the temperature difference is.
I had a question
Uh-huh.
about, so you know how we linearized VB, or we made VZ linear? Can we, like, in what problems would we do that? Like, obviously we did in this one, but like, how did you know to do that? Or how would you know to do that?
Frankly, you know only with the hindsight. Okay, so up front you wouldn't know, and you would just start solving. Okay, and I don't think it would be too much trouble. So it would just be, there was an integration here, if you remember. And that integration would not be as simple. We went from basically something VBX to x squared over 2 when you integrated, right? Something that had just x in there to x over 2. Integrating, there was essentially r minus 1 over r. So there would be one additional term to integrate here. So it wouldn't be terrible. But here it's simplified, essentially, because if this is very thin, and even though you can actually plot what the solution looks like. So it is actually that the plotting exercise that we did for quiz, if you're actually solving a practical problem, it's a good idea to plot simply to see what the difference is. If it doesn't make, like if it makes only a 5% difference in your ultimate solution, you might not want to include it. Does that make sense? So you could just go and proceed with the one we have and just integrate it, Couette flow solution, period.
Got you. Okay, so if like the difference in the two results are significant, then you want to stick with the original. Okay, right. Got you.
It's just here we already made that simplification. So we already said, look, the R is so large. So you can actually look at that other equation that is nonlinear. And for large R, it actually gets very close to linear. That's what it comes down to. If you think about this as a very thin shell and very large, so I'm like something like this, right? Then basically it looks linear, almost linear. So the difference is not huge. But sometimes it's simply also, it just simplifies your life, and it doesn't, because if it doesn't bring a lot of difference in solution, well, then it doesn't. Yeah. So up front, again, there's no, it's completely fine to just take that original one and go and integrate it. So you would integrate, there would be one term that had that R, which now becomes X, or a version of it. And the other one was 1 over R, so 1 over X. Okay, so there would be ln here somewhere. Yeah. Okay. So where was that? Again, a lot of times this really only practice tells you what to do. often you will also simplify simply, let me make that comment and put that comment out. You will simplify because there's otherwise no way to solve. In this case, I think you'd be able to, after 2 pages of integration, you'd be able to get out of it. But question is, what for? But in certain cases, you can't actually do anything. So you simplify it simply to get the first order solution. Having an analytical solution in terms of a formula, that's the quickest way possible to have a solution. Otherwise, if you can't analytically solve, then you have to go to numerical solutions, and numerical solutions are longer than just evaluating a formula, period. So, okay. So second problem is this heat conduction. So here we also had a simplification. So we had basically a zone, reaction zone with catalyst spheres in the middle of my sort of a tube or a reactor filled with spheres. And at the beginning and at the end of this tube, we have spheres that are non-reactive, that are just there to stabilize the flow, because you want to control flow as an engineer, especially if you're creating a system, you want to be in control and you want to be as close to the steady state as possible. So that's the reason for having these spheres here. So within this zone of reactive spheres, they have reactive surfaces, and that's a source of heat. So that source of heat is typically known and measured. We have some expression for the rate of energy produced per unit volume. And here's actually one example of how this, it's some constants to sometimes a function that depends on these T0 and T1. So there is some T0 that is here at the 0, and there is some temperature that the fluid enters with. So there's some normalized version. This is ultimately it's something called normalized temperature. Okay, so ultimately we have that expression typically given. Now, because of the insulation on top and bottom, this is essentially a 1D problem. Now, what I decide not to do, again because of the complications, is consider all of the complications of my fluid through this porous system. So I'm just assuming a front moving through. And that's sort of like a front that I would see if I step back and forget everything about the details of the porous medium. That's our Darcy velocity. Okay? So that's the velocity we worked with here. And the balance just gave us a relatively or deceptively simple looking expression saying dEz dz. So I only have z component because it's a 1D problem. This is my z direction, is equal to this SC, where SC is this known rate of energy produced per volume. Now my EZ has all of these terms. This is a z component of it. And essentially, we now had to work with enthalpy because my velocity of the fluid is non-zero. Okay? So essentially, I have to go and take derivative of all of these. What saves us or saves the day is that Vz we assume is this constant plug flow moving through. And then a lot of derivatives because of that disappear. So we also have to take into account what is enthalpy. And enthalpy this is a thermodynamic relationship. So basically we integrate thermodynamic relationship for enthalpy, and for ideal gas we typically take that it is Cp times T minus T0. So this is linear expression of temperature. And for fluids of constant density, we also add this pressure term. So I have both temperature and pressure term within. Now when we put that in, a lot of things disappear, and we also, so this is what we worked on last time. So we get the following equation that involves velocity, pressure, temperature, and this heat source term. So there's quite a bit going on. To further simplify, we assume that both this velocity and dPdz pressure difference are relatively small, which they should be if we are trying to control a steady state. So then we can ignore this pressure term because otherwise it complicates our life for solving this problem. And when we ignore this term as well, we end up basically with the understanding that we know what Vz is. It's a constant, it's a V0. We get an equation for temperature. Okay. And then another question is, what is this effective thermal conductivity? I'm not going to go into details of it, but basically you can find expressions for it. And also, if you actually plug in some simple function, such as the so basically, you can further normalize this. There's this theta is the normalized temperature, and you can also normalize length, that you will ultimately get the equation for normalized temperature that looks like this. And for simple functions f of this normal temperature, so this is, recall that this is that expression for SC that is presumed known. It's typically fitted to data, right? So if you fit that and put the boundary conditions in, this is how example solutions look within this zone which produces heat. Okay, so that's just so that you have a rough visualization how these solutions can look like. Okay, so some other suggested problems. So we have solved 10.2, 10.4, 10.5, and 10.6, I believe, from chapter 10. Some other suggested problems is the cooling fin problem, 10.7. 10.8 is pretty challenging, so if you're up for a challenge, go for it. But it's basically, there's flow in Z direction through a cylinder and heat transfer in R direction, radial. Okay, so those are examples of where I have, for instance, where is my pencil? Is a pretty good cylinder. So basically, if I have flow through of oil, for instance, through this pencil, but there's actually a large temperature difference. So it could be, for instance, that I'm heating this. This is something that we sometimes, when we have very viscous oil, we gotta heat it up, right? So essentially, then you will actually have radial influx of heat, which is in radial direction, and your flow is in Z direction. So your influence of velocity is in Z direction. And then you're going to get coupling in two different directions, and that's a slightly more difficult problem to solve without any further simplifications. So even if it's just for setting up the equation, if it's worth looking at, even if you don't go into solving the equation, because it's something that is a very practical problem. Heating up your tubing to move the oil along is something that is a practical issue. It's a practical problem in petroleum engineering. All right, so now we're just going to mention how equations of change look like when we don't have steady state. So we just actually have time changes as well. So this is covered in chapter 11 in BSL. So our energy balance that is really looking the same. We're just not going to say that this rate of energy accumulation will not be zero in non-steady state problems. So essentially, we proceed the same as we did in shell balances. So if I'm looking at what is the rate of kinetic energy plus internal energy accumulation within a fluid element, okay? How would I express that mathematically? Can you take a moment to think about it? Take maybe a piece of paper and try to write it down. This is not for a test or anything, just like try to test yourself. How would you mathematically write down the rate of kinetic energy plus internal energy accumulation within a fluid element? Did you get anything similar to this? Or did you get parts of it correctly? So this is my kinetic energy, plus this is my normalized internal energy, right? And then this is times volume, because these are per volume. And then the rate of accumulation will be my now in time, right? ddt. And since my control volume does not change in time, it's really ddt of the volume times this. But since my control volume doesn't change, I can basically pull it outside of these brackets. Okay, so that is what used to be 0, because we had no accumulation at for steady state problems. So now it's not 0. Okay? Now we're going to look at the energy that enters and leaves the volume through the volume boundaries in x direction. So that's actually what's shaded here. So can you write that down? This is basically shell balances. So it's the energy flux, the portion that is orthogonal to this x direction coordinate plane, is Ex evaluated at x. And I have to multiply it by the area of the shaded plane. And you need to write down what that area is. Minus Ex at x plus delta x, again, times area. Can you write that down? Did you get something like this? So again, this is the area times Ex at x minus Ex at x plus delta x. And now I repeat similar for my y direction, which is in this direction, and z direction, which is up and down. So that looks like this and that. Okay. So that is basically my balance of my combined, and this combined energy flux, if you remember, it has the convective component in there, it has work of the molecular forces, and it has my standard Fourier's law, what happens if I have a heat transfer just due to the temperature gradient. Excellent. And then I have to incorporate work done of external forces. Here I'm actually forgetting any production term, or those production terms are relatively simply added. I have to have them measured. I basically just put them times volume. They're measured in per volume. So I just, like that SC that we just had before, it's SC times volume. So I'm omitting that part. But here I'm just doing the work done of external forces. So my external forces, I'm going to label it as gravity. So it's basically rho v, that's my mass, times g, is mg dot v. Yeah, so work of any force is basically dotting it with the velocity. Excellent. So I just sum all of that up. Okay. Now this portion here, I will, just like we do in shell balances, divide everything by volume, delta x, delta y, delta z. So when I divide this term by volume, I will have it divided by delta x. This one will be divided by delta y, and this one will be divided by delta z. When I let delta x, delta y, delta z go to 0, what is this first term going to end up being? So I will have Ex evaluated at x minus Ex at x plus delta x divided by delta x. And then I take the limit as delta x goes to 0. What happens when that happens? When I shrink this little shell?
You get the negative partial derivative.
Derivative with respect to
X.
x. And then the second term, I get this very similar, it's just negative partial derivative with respect to y, and then z. So I have negative dex dx minus dey dy minus dez dz. Yes. So what is dex dx plus dey dy plus dez dz? We had something, we had a name for it. it's an operator. There's the chat. Okay. Not gradient, DEX. So gradient I would have in temperature scalar field. So then gradient of a temperature, which is scalar field, is a vector with components. So let's say that my scalar is T, dt dx, dt dy, dt dz. That's gradient. Okay. Now in this case, I have energy flux, which is a vector. So that vector has components Ex, Ey, Ez. Those are the ones that we were tracking across all of these boundaries. So my Dex dx plus Dy dy plus Dez dz is
Divergence.
divergence. And that divergence, just from this shell balance, it basically kind of tracks what's going through the boundaries in all of the directions, normal to them. Okay, so you think about divergence as basically collecting what's going on around the boundaries, normal to them. So that's divergence, excellent. And that's my second, my gradient is my first favorite operator, and divergence is the second. But again, gradient operates on scalar fields. When it operates on a field that is vector field, then I get the full tensor, like the gradient of velocity is the Jacobian, okay? And that's what results in shear stresses that are expressed with tensors. When I have vector fields, then divergence gives me just well, when I have divergence operating on vector fields, I get a scalar. So it literally kind of collects around the boundaries and just gives me a sum. Okay, so divergence relates to these basically conservation through of what's coming in and out of the boundaries. Just think about it physically that way. Excellent. Long story short, let's get to the equations. So this is this term, divergence term, and I'm going to have that the change or accumulation of total energy, both kinetic and internal, within the fluid element is negative divergence of my combined energy flux vector and plus work of the external forces. If I had any sources, then I would have plus a source here. Okay? And then this looks simple until you actually write down what this energy flux is. And this is, again, the expression for it. It's this combined energy flux. Now, if you recall momentum transfer, we had a divergence of phi, which was combined momentum, if you remember. So it's an analogous expression. It's just that the combined momentum was a little more complex because we had differences in velocity, which is vector field, and here we're tracking down differences in temperature, which is scalar field. Okay, so that was also a divergence, and that was a vector equation. This is a scalar equation. This is one equation. Okay, whereas in momentum transfer, we then had to go by x, y, z, or whatever coordinates because we had actually a vector equation, so we had to look at it coordinate by coordinate. Okay? So this is simpler only because we have a single equation that is scalar. However, it does have velocity within, so I don't know that it's altogether simpler. That's really relative. When this velocity is non-zero, then it's not all that simple. Now, where was it? So I would just like to look at one simple case when this velocity is actually zero. Okay, so I have 0, 0. I only have q here. So this is divergence of q. Okay, and velocity is 0, so this term is 0 as well. Then I have a time, the rate of change in time. What does this right-hand side, divergence of q, what does it simplify to when all of this velocity components are 0? So I have stationary solid. And my q is what? For Fourier's law. It's K gradient of temperature.
There's the Laplace.
Laplace, yes. So essentially, divergence of a gradient, if this is a constant and can come out, divergence of a gradient gives me Laplace. It's a little mnemonic to remember that. But if you remember when I mentioned Laplace equation in porous media flow, it shows up everywhere and anywhere. And this is one case where it shows up. Okay, so we have Laplace equations, just that the thermal conductivity is what actually relates it to the physics, and physically is way different from viscosity, but the equation mathematically is similar, and this is one reason to actually study transport phenomena, like all of these types of transfer all together in one course, to get that perspective that it's different, but it's not all that different. So there are certain tools that we can apply in all of the cases just the same. Okay, all right, so take a deep breath. I'm going to show you a lot of equations. Okay? So practical part of this is that, that working with internal energy is never easy. And we ultimately measure temperature. We don't measure internal energy. So what enthalpy is the part that actually enables us to boil down to equations for temperature in this case. And I'm just going to flash them at you and then present some simplified cases, like what do they simplify to. So one has to actually, this is the total energy balance, and this is what happens when I write down all of the different terms and I basically put what those velocity parts are. Now I can look at the kinetic energy balance separately and internal energy balance separately. And ultimately we can arrive at, and I'm not deriving this and I don't necessarily need you to do that, I'm just kind of showing these equations that they exist, and then you get enthalpy balance, and that allows you to simplify the equations to essentially 3 equations that are useful in practice. Ideal gases, where there's a viscous dissipation term that I'm not going to go into explaining in detail. This terminology is basically taking a tensor and another tensor and basically multiplying each position, corresponding positions, and just summing them up. So it's actually simple to compute, way simpler than any other operations. So this colon here basically signifies that operation. So that's called viscous dissipation term. So basically this is what those equations come down to for ideal gases. Now I actually have temperature, so I can simplify them to equations for temperature distribution. This is what it looks like for ideal gas. Then for stationary solids or fluids, I get this one. This is that Laplace term. And again, there's a source term here that I didn't have initially. Now I just included it for complete set. So basically, this is something that you can use a lot and you can directly apply. And then for incompressible fluids, I get something like this. And there is tables in the appendix that help use these in different coordinate systems. So ultimately what it comes down to is that you can always use the appendix just like in momentum transfer and plug in all of the terms, look what is zero. We will often really work with steady state. So the variations in time will be zero. Okay? So you can either use shell balance as a way to solve the problem or use the ready-to-go formulas. Depending on a problem, that's not always what makes it easier, just having ready-to-go formulas. Ready-to-go formulas make it definitely easier if you actually have a solver and you want to solve problem numerically and solve more generic problems that you can kind of always apply the same equations. Okay, right. So this is basically we're going to end up with for heat transfer, and next time we're going to start mass transfer.
I had a question. It's not about the content, but I was wondering if you're gonna post like you know how you have those appendixes of equations? I'm assuming there's those for heat as well.
Yes.
Or can
there
you
are.
post that? My book doesn't have those appendixes, or it's not the same. They're actually it just gives us like what the what's it called the calculus, like what is divergence, what is Laplace. It doesn't give us those.
So your book, so if we go to momentum transfer, your book doesn't have appendix B5, B6, and so forth?
Yeah, in the back. The appendix is supposed to be in the back of the book, right?
Right. So would it be useful to you if I just give you a PDF then?
Actually, you know what? I just realized I was looking in the wrong section. I found this.
Okay.
Never mind.
It's a complex book. So frankly, just learning to navigate it is non-trivial. And that's the case with any book on transport. Just learning where the formulas are and learning how to get to them when you need to solve the problem is part of the training, if you will. So again, I can definitely post a PDF. If anybody has a need for PDF, just email me. How about that? Okay. Not that I should publicly say, I found it on internet. So it exists out there. So in this case, we would go to, there's 4 Newtonian fluid. There is, now I'm just gonna show it this way, but there is its B5. It's easier if I say, even if I show it on screen, the font is too small. So there's appendix B9 that gives the relationship for Newtonian fluids, which is what we will most of the time have in the case of solving. And then you have to go to appendix B7 for some of these terms. So you have to combine essentially appendix B7 and B9 for Newtonian fluids. Okay? And those are ready to go for formulas for temperature distribution. Okay. Any other questions? Okie dokie. Well, enjoy the rest of your Monday. I will stay online if you would like to ask questions for the office hours. Otherwise, I see you on Wednesday.
Hi, Dr. Pradanovich.
Hello.
Can you hear me?
Yes, I can.
Okay. I had a question over problem 4 on the homework that was due this morning. Whenever I tried solving it, it's like I got really stumped towards the last portion of it. And so I wanted to know if I could just like work it out with you just to see if I can like understand the problem a little better.
So do you want me to allow you to share the screen? Would that be useful?
Yes, that would be greatly appreciated.
Let me just figure out. Stop share. All right. So I stopped sharing mine, and I think you can share now.
Okay.
Michael, do you have similar questions or? It's still online, but I don't think
similar questions.
Okay.
I have no idea which one is.
Well, now is the time to learn.
Yes.
We're gonna live inside Zoom software for a while, so take your time.
I think it seems that I was a little bit behind where Victor's at. So I got to the point where I'm equating the heat transfer between the mantle and the surface and the core and the mantle. But I wasn't sure how to set up the system of equations to solve for the unknowns. That's where I got a bit confused.
So this is rather similar, other than the coordinate system. It's rather similar to the composite problem, 10.6. Yes, so we solved that composite in class. We solved it for the oh, there we go. Now
Okay.
I can see here.
So let me see if I can. How do I get into the little? There's. So. So we were given the core radius. Let me see. Where? Oh, is it? Oh, okay, there it goes. So that did not work. Let me double check.
You can try it with the mouse, I think.
Okay, there we go. So, given that, given the temperature of the inner core, which was constant, that should be kilometers. We're given the radius of the outer core, and then the radius of the mantle at 6370, and then the radius of to the surface, which was 64, and then the temperature being 280 Kelvin, and then
It's pretty impressive writing with a mouse, by the way.
Oh, thank you.
I need a pen for that, but okay.
All right, yeah, no, I have a little drawing pad and a little pen, so it's as close as I can get to.
Yeah, I can't write with the mouse to save my life, but anyway. Okay.
And so with the shell balance, since it's just the area, or the change in, or I guess the change in area times the area times the change in radius, since that's really the only thing that's going to be changing.
Right. So just to understand these problems conceptually, when I have multiple, just like I have my two hands, let's put something else in between. So I have multiple materials in contact. Okay? And all of them are providing certain resistance to flux. So you can either look at them from the conductivity perspective or resistance perspective, which is 1 over resistivity, right? Okay. So when we did this in class, we basically equilibrated a composite material in Cartesian coordinate system. So ultimately, to equilibrate through this system, you basically get the same flux through its steady state, correct?
Yes.
And flux is something that is per area per time, right? Now, in the problem of the cylindrical nature or the spherical nature, what changes and why I need these radii, okay, to know how much resistance I have, but also what drives this problem is the temperature at the core is 5500, the one on the surface is 280. That's the temperature gradient that is driving the problem, right?
Okay.
So I'm going to have things coming out. But as I'm coming out, this is spherical, right? So as I'm coming out in larger radii, my flux per area has to be smaller. because
Okay.
flux is per area, and area in that coordinate system is getting larger and larger and larger and larger as I go through, right?
Okay.
And that's why basically my balance, I hope when you were balancing this, you get something like DDR, R squared QR is equal to 0.
Let's see,
Right?
because this is what I had written down, and so I had gotten that it was the 4 pi r squared QR
Yes.
Over r, or at r, minus 4 pi r squared QR at r plus delta r
Right.
plus 4 pi r squared delta r, the SE being equal to 0 since it's steady state. And then we can go ahead and just ignore
Yeah, 4
or
pi,
cross
yeah.
off those 4 pi terms.
Yes.
And so that leaves us.
So if I were to divide by the basically delta R, which if you were dividing by volume, that's what you would get. Basically, this first two terms give you minus DDR. When you take the limit, when delta R goes to 0, it gives you minus DDR of R squared QR.
Oh, okay. So,
Right?
and then
R squared
QR
is equal to
then
0. And that means that R squared QR is a constant, and that constant is same everywhere.
Oh, okay. So I see. I
That
made a.
constant was called Q0 in the problem that we solved in class. Remember? So then you can go and then basically do and your QR is K D or minus K DTDR, right?
Oh, okay. Because
Is the
I
R
just noticed that.
component of the gradient.
I did just notice that in my little thing, I kept the little SC term. I guess
Yeah,
with that
SC here, you don't need that.
Oh, okay. So, okay, I'll be sure to note that.
Yeah.
But let's see. And you said that the QR.
Well, SC, when you have it, it's given. It's not a big deal to deal with.
Oh,
right?
okay. That makes
it's a source term.
so much more sense.
Yeah. And frankly, technically, you could deal with the same problem by formulating it as having a source in the middle, right? That would essentially result in this temperature of 5,500 Kelvin at the middle, right? Right? Because that's constant source within that causes that temperature. So mathematically, you can express as a boundary condition that this temperature goes from this value to some other value, or you can throw in a source term in there that is constantly keeping it at that temperature. Does that make sense physically?
Yes.
Yeah.
Let's see. And so, continuing with this, multiplying both sides by dr, and then doing the
What
integral.
I'm saying when I'm saying when I'm saying that derivative is 0, I'm saying that R squared QR is constant, really.
So it would be something.
And yeah, and that constant seems to be happening. It's happening throughout if I equilibrate it. So that constant is same everywhere.
Okay.
So what I want you now is to kind of look at the problem that is solved in class. So so you need to now express QR in terms of temperature because your boundary conditions are in terms of temperature.
Okay.
And then you have to, first things first is that constant is throughout, and that's essentially saying that your flux per area is same everywhere, right?
Okay.
And then the second part is you need to have, so basically that's your continuity of flux at any boundaries of different materials. And what's going to be then how these K0, Km, Kc will come into play is that this QR that you have it's a minus constant dTdr, right? Derivative of temperature.
Mhm.
And that constant K is different in every different material.
Okay.
And then you have to stack them together, right? And they have to have same temperature at the boundaries.
Mhm.
Right? So there is, just like we did in class, the boundary of the material, from the left side, you have one material with one type of K, and on the other side, you have a different material with a different type of K. So you write down those equations and then kind of try to simplify them.
Okay, so let me see if I'm understanding this correctly. So let's say on the boundary between the outer crust and the and at the mantle, since those two are touching, it's like they'll have the same thing. And then given from here with this constant, if we sub in the QR being equal to negative K dTdr.
Right.
Let's see.
And
what
that K is different in different materials. So on one side of the material, you have one K, on the other side of the material, you have the other.
Let's see. So that would work out R squared K dt dr being equal to C1 multiplying both sides. I guess I should probably move everything over. So R squared K, and then integrate that. Will leave us with T being equal to negative C1 let me know, positive C1. Oh, that was not R squared, but
Yeah, so yeah.
it is not letting me, oh, okay, there it goes. Okay. R, and then some K. And then that, just double checking, that's what that T should be. And
Something like that, yes.
Okay.
And then you will integrate, so you can integrate between the radii that you have of the material, right?
Mm-hmm. Let's see. Wait.
So you will integrate between, there's this first one starts at 1200 kilometer, right?
Oh, okay. And so
to, what's the next one? 35, and then 35 to 6370, then 6370 to 64. Okay. Yeah.
And so going back to where, since the
and
outer
that
core,
K, yes, at K and that temperature is that KC, right? The core.
Mm-hmm. Let's see. So this would be, so for figuring the outer core, since its temperature isn't constant, would I have to go from the radius from the inner core to the outer core,
So,
or am I allowed? Or
if I believe we're keeping at the outside, we're keeping 280.
Okay.
Yeah, so it's constant at that radius of the Earth.
It's not being too friendly with me.
Right.
Okay.
Better than I expected, so so there's that.
So, let me see if I can find the. Okay, there it is. What did we say the radius was again for the outer core?
You had it written up there.
Oh, so it would just be that 3,500 kilometer. I'm just gonna put RO that way, since I'm already bunched up in the corner, and then times K. I think we said O was what the problem
C
said
core?
for.
Oh, this is already outside. Yeah, K outer.
Then this being equal to C1 radius of the mantle, and let's see. And just double check, or because it's like I just noticed. So I'm a little unsure since I have. It's like I have written down that C1 exists on both of these sides. So would that mean I would be able to solve for C1 in a general sense, and then apply that to?
Well, you will still have to. This is a difference. If you integrate temperature, you will have a temperature difference.
Oh, okay.
So then you have to go and basically stack them up. So there will be temperature difference from the outside TO minus the one at the radius, the M. So T0 minus TM, TM minus TC, right?
Okay. Okay.
And you basically, yeah, and you can basically, and then in each of them, those temperature difference is some expression of K, right? That has the radius and K in there. Also integrated between the two different radii. Let me show you the system. May I share?
Yeah. Okay. I think
Did you get the conceptually though? I mean, you need to sit down with the.
It's like I think I have the concept down because it's like
if you work through the basically it's a very similar to the one that is cylindrical coordinate system where I asked you to rework the example that is done in class, right? So the only difference that really changes is that slightly there's this difference R0, right? And the fact that the constant, what's constant is R square Q R, right?
Okay.
So that, because I have to kind of multiply by area as the area is changing. And in cylindrical case, what was constant was R times QR.
Okay.
So if you go just like walk through, and again, like in the, there was that was example 10.6.1, and that was part of the homework, right?
Yes.
So
yes.
we were kind of going in progression, and all I changed, all I changed was the coordinate system, which is not trivial. But what's now constant is instead of R QR, now it's R square QR.
Okay.
But the integration steps and the system of how you stack them up, ultimately you have like temperature at one side minus temperature at the other, is so you just have to stack them up, and you will get some expression that is dependent on all of the K's and all of the R's in there, like as a sum. Right? And that's what so if you look at the equation 10.6.9, that was the expression for cylindrical system. And the difference between this problem and that, I don't think, if I recall correctly, that we actually looked at the Newton's law of cooling, because for Earth it can be ignored. So that H in there, you might or might not have it in there. That's all.
Okay. Because that was another.
But that's just a difference in how you apply boundary conditions.
Okay, because it's like that was it's because what I ultimately got, or what I have written down was that the temperature of the core minus the temperature of the surface being equal to some Q naught.
Sums of Q's and K's, right?
Yeah, and so I just didn't know what to do. It's like I didn't know what I didn't know what to do with HC or HS at that point, since it was never really specified. But if it's
not specified, we're just assuming they're not there. Okay. So the difference for Newton's law of cooling, it says that if I have my hand next to the air, then basically they don't equilibrate at the same rate. Basically, the thermal conductivities are off by order of magnitude. So I cannot assume, even if I'm keeping the temperature of the air next to my hand, even if I'm keeping it constant, that doesn't immediately transfer to my hand.
Oh, okay.
Right? Now, that's what Newton's law of cooling is saying. But like in this case, I don't believe we put that in. So basically, it's ignored.
Okay.
Like in the general scheme of events, that's the minimum of your problem. Transfer between the air. So you can, if you actually, or basically, if you have measuring the temperature at the, I have a little probe that goes into my hand, and I know what my temperature at the edge of the hand is, then I don't have to take care of the air.
Oh, okay.
That
That
transfer
makes
to the air, right?
Okay, that makes a whole lot more sense,
Right.
and that like completely.
That's important. That's important to understand in these problems, like how are boundary conditions given.
Okay.
So if somebody is saying, hey, your temperature of the hand at the edge of the hand is this, then your problem is simple. You don't care about the air.
Okay.
And any kind of Newton's law of cooling between fluid and solid.
Let's see.
But depends what you measure in any problem.
Okay, because that clears up a whole lot of my issues right there.
You don't have H's. Yeah.
Okay, because it's like I had the H's in there, and it was just I didn't know what to do with them. It's like I had everything else in there, but that lets me solve for the temperatures at those boundaries.
And it's literally saying you have a temperature probe on inside the Earth.
Oh, okay. Okay, I think that clears up.
Who cares about the air? Okay. There's atmosphere, but who cares about it?
Okay, I think that clears up a whole lot of everything that I had about that problem. Okay.
Yeah, well, it's a practical. The Newton's law of cooling is it's a pain in the I can't figure out. So James, does this discussion clear any questions for you?
A little bit.
But do you have questions from before that?
I'll share my screen real quick so you can see kind of where I was at.
So also, before I forget, if you want a solved practice in the, let me see which that problem is. It's just a slightly different problem, but it gives you a little bit of a spherical. There's a, is that viscous heat? No. There's a heat conduction. Yes. So just deriving this spherical coordinate system, 10.3. There's a spherical nuclear fluid element, and that one has a source within, but you can just set that source to 0. And that's just with that can give you practice in spherical problems. It's a variant with the source term, but you can set source term to 0 if you just wonder how to derive equations. Okay, share the screen.
Okay. Can you see the screen?
Look at this. Oh my goodness, that is pretty. I will write this neatly when I grow up, which is never. Okay.
Can you hear me right now?
Yes.
Okay. Sorry. So I did that first part that we were talking about with Victor, and I got to this point, and then whoa, I don't know what happened there. Sorry, that was weird.
That's okay.
And then I tried to apply the boundary conditions, and this is where I got confused. So I went down here and set the boundaries equal to each other. So the core is equal to the mantle, and the mantle is equal to the surface. Correct? And then I wasn't sure where to go from here.
So from here, basically, to get the expression that ties you to what you know and to get those constants, you want to express, or put things or plug things in sequence so that you get just the core minus. So there's core minus that there are two intermediate ones, whatever, mantle and outer core. So you want to do core minus first one, then the first one minus second one, and second one minus third one, right? When you stack those equations up, you can show what is, so express what is your T, this innermost one, core, minus T the next one.
Right.
And then your T next one minus next one is equal to something. So when you add those equations up, you will get core minus the outermost one.
Okay, so it would be
as an addition of all of the terms.
Together, when you add them together, it's the TC minus the TS there.
Right. So you call them, okay, you call them in sequence. So basically you will get first equation gives you T0 minus T1, right, is equal to something in terms of the K, this core thing. And then T1 minus T2 is something with the Km. And then T2 minus T3 is something at the end. So when you add those up, you will get T0 minus T3, and you have T0 minus T3. You have T0 and you have T3.
Okay.
Yeah?
Yeah.
And that's how you get out of that.
So I just needed to carry out what I did a little bit further to get to that point. Okay.
Yes.
Okay. Thank you.
And then this flux that you're comparing with the others, this Q you can get from any of those terms once you work out.
Mm-hmm.
Yeah?
Yeah.
And then that's the flux that heat flux that we compare to the one in petroleum engineering. And that's just an exercise in conversions and conversions of the units used, and just what is the relative flux indeed.
Yeah. Yeah. Okay.
So, and you want to compare to that flux because this flux through Earth is going on regardless, right? So you want to kind of compare the relative difference.
Okay. Thank you.
Sorry for the pain, but it is an interesting problem. You gotta admit that.
No, yeah. And I know we've talked about it before. The class is super interesting. It's just difficult.
And that's just what is. So
yeah,
it's difficult for you, it's difficult for everybody else. It's not the same.
Yeah.
Equal opportunity difficult.
True. All right. Have a good day.
You too.
I'll be in contact if I have any more questions.
Sure.
But I think that
and then we'll just work it out sometime today and submit.
Yeah, no, because it's like I definitely do want to go back in just in case a question like this comes up.
And again, if you again want to exercise this with 10.3 as a problem that has a spherical coordinate system.
Okay.
Just to kind of, and just a slight variant so you can see whether you understand.
Okay, I'll be sure to do that then.
Mm-hmm.
All right. Thank you so much for helping me out.
All right.
Alrighty. See you
Wednesday. Have fun. Or try to.
Bye.
Bye.
Bye.